Today we're going to do a true training-style breakdown of HACCP hazard analysis, the part of HACCP that most people struggle with. And honestly, it's the part auditors care about most because hazard analysis drives everything: CCPs, limits, monitoring, and your records. A lot of HACCP plans look good on paper but fail in real life because the hazards don't match the process or the controls aren't realistic. So in this video, I'll show you how to think through hazard analysis step by step, using a realistic example and the same logic you would use in an audit. Hazard analysis is not just writing biological, chemical, physical, and filling a table. Hazard analysis is a structured decision process where you do three things. 1. Identify what hazards could reasonably occur at each step. 2. Decide which hazards are significant, meaning they need control to prevent illness or injury. 3. Document the controls and whether they're controlled by PRPs or require CCPs. A good hazard analysis reads like a logical explanation of your operation. When you can explain it clearly in plain English, auditors typically have confidence in your system. Before you do hazard analysis, your HACCP plan must have three things correct: product description that includes ingredients, packaging, shelf life, and storage conditions. Intended use: how consumers will use it and whether it's ready to eat. Process flow diagram: the actual steps that happen in your facility. If your flow diagram is missing a step, like staging raw materials, rework, relabeling, or holding product, your hazard analysis will miss hazards too. This is why auditors often walk the facility and compare what they see to your flow diagram. For this training, we'll use a realistic product: refrigerated bottled fruit juice. It's ready to eat and consumed without a kill step by the consumer. That means biological hazards matter a lot, because if pathogens enter the process and you don't have an effective kill step, your controls must be strong in other areas: sanitation, temperature control, shelf life, and supplier controls. Also, because it's bottled, physical hazards like packaging fragments and equipment where can be relevant, and chemical hazards like allergen cross-contact or sanitation residues must be evaluated. Let's define hazards in a practical way. Biological: anything living that can cause illness, pathogens, viruses, parasites, and sometimes toxins produced by microbes. Chemical: allergens, cleaners and sanitizers, lubricants, pesticides, and unapproved additives. Physical: foreign objects that can injure, metal fragments, glass, hard plastic, stones, wood. In real hazard analysis, the question is never, is it possible somewhere on Earth? The question is it reasonably likely to occur in this process under this facility's controls? In a real HACCP, significance is typically based on severity: if it happens, how serious is the harm? Likelihood: how likely is it to occur, given your process and history? Control: do you already have effective controls in place? A hazard becomes significant when it's both serious and reasonably likely unless controlled. This is where many HACCP plans fail. They either mark everything significant, which creates too many CCPs, or they mark almost nothing significant, which looks like they don't understand risk. Auditors look for balanced, justified decisions. They want to see that you understand your real risks and that controls are appropriate. The risk score is calculated by multiplying severity by likelihood. For example, a hazard with a severity score of 3 and a likelihood score of 2 results in a risk score of 6. In this example, hazards such as pathogens in fruit and metal fragments score higher and may be considered significant, while hazards with lower scores may not require the same level of control. The key point is not the exact numbers, but the logic. This type of scoring helps prioritize hazards and supports consistent, documented decision-making during hazard analysis. Now we'll move into the real work of hazard analysis by process step. I'm going to walk through a typical juice manufacturing process, starting with receiving, followed by raw material storage, washing and sorting, juicing and blending, and, when applicable, pasteurization or another kill step. From there, we'll look at filling and capping, cold storage, and finally distribution. At each step in the process, we'll identify realistic hazards and the controls that are actually used to manage them. Receiving is often one of the most important steps in the process because it's where hazards first enter the operation. Many food safety risks originate at receiving, which is why this step deserves careful attention during hazard analysis. From a biological standpoint, raw fruit can carry pathogens from the field environment. In addition, if water, ice, or other ingredients are received, those can also serve as potential sources of contamination. The level of risk depends on factors such as the type of fruit being used and the effectiveness of supplier controls in place. To manage these biological hazards, facilities rely on controls such as a supplier approval program, supplier documentation, and thorough receiving inspections. In some operations, testing programs may also be used. However, it's important to understand that testing by itself is not a control. It is a form of verification that supports the overall food safety system. Chemical hazards must also be considered at receiving. These can include pesticide residues when suppliers are not properly controlled, or allergen-containing ingredients entering a non-allergen processing line. Even though juice products are often non-allergen, many facilities handle multiple products, and the potential for allergen cross-contact must be evaluated. Controls for chemical hazards include detailed supplier specifications, approved supplier lists, a documented allergen control program, and certificates of analysis when applicable. Physical hazards are another concern at receiving. Stones, stems, hard pits, or packaging debris can be introduced with raw materials and carried further into the process if not addressed early. These risks are typically controlled through visual inspection, sorting, and, depending on the process, additional controls such as filtration or straining later in production. A key training point to remember is that receiving hazards are often controlled through prerequisite programs. However, the hazard analysis must clearly explain the logic behind those decisions, what the hazard is, why it matters, and exactly how it is controlled. Storage and staging is an area where facilities often experience deviations, and it's a step that can easily create risk if it's not well controlled. From a biological perspective, many fruits and juice ingredients are temperature sensitive. Improper storage can allow microbial growth, especially when product sits in a warm staging area for extended periods of time. These biological hazards are controlled through cold storage temperature controls, FIFO practices, defined limits on staging time, and documented monitoring to verify that conditions are being maintained. Chemical hazards must also be considered at this stage. When chemicals are stored near ingredients or packaging, there's a risk of contamination if proper segregation is not in place. Controls for chemical hazards include chemical segregation, clear labeling, employee training, and sanitation standard operating procedures. Physical hazards can also occur during storage and staging. Damage to packaging or containers during handling can introduce debris into the process if it is not identified. These hazards are controlled through good handling practices, routine inspection, and rejecting damaged materials. From an audit perspective, this is often where auditors ask for evidence. Questions like, "Show me your temperature records," or "Show me how you control staging," are very common. If your hazard analysis says a hazard is controlled by refrigeration, you must have real records to support that claim. Washing and sorting can help reduce hazards in the process, but if these steps are not properly controlled, they can also introduce new risks. From a biological perspective, wash water can spread contamination rather than remove it, especially when water quality is poor or when water is reused without adequate controls. This is why effective potable water management, a strong sanitation program, clear standard operating procedures, and proper maintenance of wash systems are essential controls at this stage. From a chemical standpoint, the use of chemical washes introduces the potential risk of chemical residues remaining on the product. To control this hazard, facilities must ensure correct chemical concentrations, include rinse steps when required, provide proper employee training, and perform verification checks to confirm the process is working as intended. Physically, sorting plays an important role in removing stones, stems, and damaged fruit that could otherwise contribute to physical hazards later in the process. These risks are controlled through visual inspection, defined sorting standards, and routine equipment maintenance. It's also important to clarify a common misconception. washing is not a kill step. While it can reduce certain hazards, it does not eliminate them. For this reason, washing is typically managed as a prerequisite program, or PRP, rather than a critical control point. Juicing and blending is a step where contamination can occur quickly because product surfaces are broken open and exposure increases. From a biological standpoint, pathogens can be introduced through unsanitary equipment, poor employee practices, or cross-contamination between batches. When equipment is not cleaned effectively, the risk of biofilm formation also increases. These biological hazards are controlled through sanitation stops, validated cleaning procedures where needed, good manufacturing practices, employee hygiene, and environmental controls. Chemical hazards must also be evaluated at this stage. These can include lubricants from equipment, cleaning chemical residues when rinsing is inadequate, and allergen cross-contact when shared equipment is used for allergen-containing products. Controls for chemical hazards include the use of food-grade chemicals, a preventive maintenance program, allergen changeover procedures, and proper line clearance. Physical hazards may occur as well, such as metal fragments from worn parts, broken gaskets, plastic fragments from scrapers, or hard pieces from damaged equipment. These risks are controlled through preventive maintenance, pre-operational inspections, filters or strainers, and in some cases, metal detection, depending on the product and packaging. A key training point to emphasize here is that most hazards in HACCP are controlled through strong prerequisite programs, which is a fundamental reality in food manufacturing. Here's a critical HACCP decision point. Does your process include a validated kill step, such as pasteurization? If there's a kill step, that step is commonly identified as a CCP because it is specifically designed to control biological hazards. In this case, your hazard analysis should clearly show that pathogens are significant and that they are controlled at this CCP. You would then define critical limits, monitoring activities, corrective actions, and verification procedures for that step. If there is no kill step in the process, the hazard analysis must demonstrate how biological hazards are controlled without a CCP. This is typically done through a combination of supplier controls, sanitation programs, cold chain control, shelf life studies, and in some cases, product formulation factors such as pH. It's important not to claim a CCP exists if the process does not truly control the hazard. Auditors will challenge unsupported CCPs. In real-world practice, many refrigerated foods rely on strong prerequisite programs, cold chain control, and shelf life management rather than a traditional kill step CCP. But the justification for this approach must be clear and well documented. Packaging is a common point in the process where hazards can be introduced if controls are not properly applied. From a biological perspective, post-process contamination can occur when the filling area is not adequately controlled, when caps or bottles are not properly protected, or when employees handle packaging components incorrectly. These biological hazards are controlled through hygienic zoning practices, effective sanitation, container handling standard operating procedures, and good manufacturing practices. Chemical hazards must also be considered during packaging. These can include sanitizer residues if bottles are treated incorrectly, or the use of incorrect packaging materials. Controls for chemical hazards include approved packaging specifications, sanitation procedure controls, and proper line clearance. Physical hazards may also occur at this stage, such as cap fragments, packaging debris, plastic shavings, or broken parts. These risks are controlled through inspection, equipment maintenance, and in some cases, final product screening controls, such as filtration earlier in the process. For refrigerated juice, cold storage and distribution are critical steps in the process. From a biological standpoint, temperature abuse can allow microbial growth and shorten the product's safe shelf life. These risks are controlled through continuous or routine temperature monitoring, alarm systems where applicable, documented checks, and clearly defined corrective actions. Chemical and physical hazards are less common at this stage, but they can still occur. Packaging damage during storage or transportation can lead to contamination or introduce physical hazards. Controls for these risks include proper handling procedures, pallet inspection, and rejecting damaged cases before distribution. From an audit perspective, This is where auditors often ask to see cold storage records and shipping temperature requirements. If your hazard analysis relies on refrigeration as a control, you must have evidence to support it. Now let's make this practical. In your hazard analysis table, every significant hazard must be clearly linked to a control. Those controls generally fall into three categories. The first is prerequisite programs, or PRPs. These include good manufacturing practices, sanitation programs, supplier approval, allergen control, pest control, maintenance, training, and calibration. PRPs manage general operating conditions across the facility. The second category is operational prerequisite programs, or OPRPs. OPRPs are used when a specific hazard requires tighter operational control, but the step does not meet the definition of a CCP. These controls are monitored more frequently than PRPs and typically use action limits rather than critical limits. The third category is critical control points, or CCPs. CCPs are specific steps in the process where a critical limit is measured and controlled to prevent or eliminate a hazard. A common mistake is identifying too many CCPs. A more effective approach is recognizing that PRPs and OPRPs control most hazards, while CCPs are reserved for the few hazards that require a measurable, non-negotiable limit. Auditors typically focus on three key things during a review. First is alignment. They want to see that your hazard analysis matches your process flow diagram and what they actually observe on the production floor. Second is justification. Auditors look for clear, logical explanations behind your decisions, especially when hazards are identified as significant or not significant. Third is evidence. They expect to see records that prove controls are being implemented, such as sanitation records, temperature logs, training records, and preventive maintenance records. If your hazard analysis states that a control exists, but there are no records to support it, that is considered a red flag during an audit. Common mistakes in hazard analysis include copy-pasting hazard tables from another facility, listing hazards without clear reasoning, and treating every identified hazard as significant. Other frequent issues include missing hazards that are clearly relevant to the process and failing to update the hazard analysis when changes occur. The most effective hazard analyses are simple, realistic, and clearly tied to how the facility actually operates. Hazard analysis must be reviewed whenever there are changes to ingredients or suppliers, equipment, packaging, process steps, cleaning chemicals, or production volume and scheduling that could affect cross-contact risk. In addition, best practice is to formally review the hazard analysis at least once a year, even when no major changes have occurred. Auditors commonly ask, when was it last reviewed? If the process has changed but the hazard analysis has not been updated, this will likely result in a nonconformance. Hazard analysis is the foundation of HACCP. When it's done correctly, the rest of the system becomes much easier. CCPs are clearer, controls make sense, and audits go more smoothly. The goal is not to list everything that could happen in theory, but to identify what could reasonably happen in your process and clearly show how those hazards are controlled. If you're looking for practical templates to help structure your hazard analysis and HACCP documentation, you'll find a link in the description. Subscribe for practical food safety training, and leave a comment with the HACCP topic you'd like to see next.